Yeah, so the last time what we had done is we did understand about the vector operation, and the point is like there were two different kind of pullings over there which were done. One was called as spatial pulling, another was called as orientation pulling. And the purpose of this orientation pulling was essentially to get down a vector field created out of that rotated versions of convolution. Now, what it did is in the last class, you knew essentially like how to go from a scalar field to a vector field. But now comes down the next part, which is like how do you go from a what do you call as a vector field to a vector field? That's a question over here. So the issue is like in the next layer, when you come down, so you have this kind of a vector field which is made available to you. So say, is it updating? Are you able to see it?
Yes.
Yes, sir.
I mean, for the last few days, I mean, in the yesterday and day before yesterday, this Jamboard was a bit lagging. So in case you are not able to see it, then just prompt me that it's not refreshing somehow. Now say that these are my vector fields over here, like this, which keep on going. Now this vector field is something which I call as Z. So essentially what is happening over here is that any given location which I can write down as Z, which is a vector field at an alpha comma beta location is essentially composed of vectors along all the channels over here. So say this is channel. So then this will be composed of a vector along alpha beta 1, or if we go by our convention of writing where I have the channel number coming first, this will be 1 comma alpha comma beta comma another z vector which is along 2 comma alpha comma beta. Like this it keeps on going till another last vector along c comma alpha comma beta. This is what it should look like over here. Now, if I want to convolve, essentially that convolution kernel is also going to be a vector field. Okay. So my convolution kernel is going to look down something like this. Okay. Now I can have rotated versions of it. Like this it keeps on going till some rotation by theta n, which is going to yield this whole thing. Okay, and now I'm looking at a convolution operation between them. So how this convolution operation is going to work out is pretty interesting. So what you are going to do is, so as a result of this convolution, so let me just complete it. As a result of this convolution, what you are going to get down is some sort of a set of scalar fields. Okay, and then this is my theta direction. You do a orientation pulling. And then you end up getting your vector field over here. And you keep on repeating this for all the other convolution kernels which will come down over there. Then you get your output. Now the question is, how is this vector convolution going to work out? Because what I said is that your this input field is a vector and your convolution kernel over there is also a vector. Okay, so let us represent this one. So my input, which is a vector field and a multi-channel vector field. That's something you need to keep in mind. So input is this Z. This is a multi-channel vector field, okay, obtained from a vector convolution layer. This convolution kernel over here also needs to have the same number of channels, and this is also a vector field. This is something we called as W. So your convolution kernel is also a learnable multi-channel.
Not getting updated.
Sir, I
Sir,
think
it's laggy.
it's not updating. Hold on. I'm on the right slide. Huh. Vector field. Okay, so now what I'm going to do is I will be representing this operation as said convolution with W. This is what I want to represent this one as. Now this thing can be written as ZU convolved with WU, okay, plus ZV convolved with WV. Okay. So what these represent over here, this one which is U is the horizontal component of the vector, and this is the vertical component of the vector. Now definitely if the first one is the horizontal component of the vector and the second one is the vertical component of the vector. So if I have a operation which is given over here, which is sort of akin to what a dot product operation is, then the output will definitely be a scalar quantity. So this one, this leads to the output be scalar. Is it so? Do you agree with it?
Yes, sir.
Yes, sir. Okay. So now essentially what I'm doing is that I am no more representing my vector field in terms of a r theta vector or a or sort of like a magnitude and direction vector, but now I have started representing it in terms of its components, and from there I do it. So now if I do that, then comes the next question as to how do I really do my back propagation over here. Okay. So this rule of back propagation is going to be pretty straightforward. It will apply to all of these over here. So now what happens is that you had, so what we said was that you had your input, which was this Z, and then you were convolving it with rotated versions of that W. So this is W, this is W theta, let me see, what do I call that as W theta 1, okay, theta 1, this is W theta 2, this is W theta some n. Now, when I convolve with each of them, I'm going to get down a scalar field, and this is a 2D scalar field which I get down from here. Then what do? I take all of them and do a orientation pooling, and as a result of it, I get down a vector field. Okay, and so whatever this vector field say, call this y for convenience sake. Okay, so now the point is that when I want to do this back propagation, how am I going to? So we always said that because essentially this is my principal kernel. So all of these are derived. These are like rotated versions of that. You don't have those values being stored in any way. On the runtime, you are just going to rotate them and get them. So you need to during backprop values only in W are updated. Values in W theta n are not stored, but they are derived from W during forward pass only. Okay, so if that is the scenario, then what will happen is that when you are trying to do a back propagation, you will be getting down gradients coming down from each of these roots. Okay, now say that for a certain component, okay, corresponding to a kernel rotated by theta n, say the gradient is nabla w, nabla w theta n, say, then what you can get down is you can write down that nabla w, which is that actual update on w, is going to be equal to an expectation, or basically an average operation, an expectation over all theta 1, theta 2 up to theta n of, you will have to now transform this one with a negative of this minus theta n times nabla w. So what I am essentially saying, nabla w theta n. So what I am saying is that rotationally compensate for the gradients before they are updated. Okay, so are you getting this point? Why do we need to do this rotational compensation over here during the backward propagation? Did you guys understand why this is to be done?
Hello, sir.
Sir, but why are we not calculating the del W from itself? Like we are also using W, then we can calculate the del W from the back propagation itself. Then why we're taking the average expectation value over all the theta?
Okay. So let's come over here. So what is happening? You have this y over here. Now this is derived from this set of scalar fields which go through orientation pooling. So now during backpropagation, what will happen is this will come over here. Okay. Now what is this orientation pooling is doing? So at every single location in the same spatial location, it scans across all of them. Wherever it finds a maxima, it will place that value over here. And then the angle of this one is the same as which angle it comes from, whether it's coming from 0 or theta 1, theta 2 up to theta n. That is what it was doing. So for every single location over here, it will actually be going back to a point here. Okay. Oh, just a minute. I
Yeah.
think I made a mistake. This should not be expectation. No, I recall. This should actually be summation. We'll come to it. Why summation? Summation because it's a sparse matrix over there. So now essentially what's happening is this location say may come from here. This location comes from here. This location comes from say maybe here. This location comes from here like this. So every single location will go and put itself at only one point. So if this one is coming from here, then that corresponding location over here, here and here are going to be getting down zero values in terms of gradient because it
Okay.
did not come from here.
Oh, okay,
Okay.
sir. Okay, sir. I got it.
So now in that gradient field which is present over here, so corresponding to each of this you will have a delta W. So this is delta W0, this is delta W theta 1, this is delta W theta 2, this is delta W theta n, like this it is going to go. Then they are going to impact over here. Now the point is these when they get impacted is of no use. Essentially I want to impact this one. And how do I want to impact this one? For every single location I need a delta W. So this one also I will have to rotate. This one I will have to rotate. This one I will have to rotate and appropriately compensate. Then I get my delta W field which comes and impacts this one. Because these things over here, they anyways are not stored. They are just generated in the runtime.
Yes, sir. Yes, sir.
Okay. So is this clear?
Yes, that's clear.
Okay, good. Uh, hmm.
And sir, we are using just the basically we are using the rotation to save the memory time, right? So to save the memory, because we are not storing those W theta 1, W theta 2. The purpose of doing this kind.
See, there are two purposes. One is that the reason you are not storing them is not essentially memory. That is a consequence of not storing it that you are saving out on memory. But the reason for not storing it is because you want rotational manifestations across the kernels itself.
But sir, if we just randomly create, just generate the parameters for and each of them kernels, and then when if there is some rotational significant features there, then automatically those features will be updated in the back propagation itself, right?
Okay, now tell me if you do that, then how will you enforce that W theta 1 is a rotated version of W by an aspect of theta 1? How will you ensure that?
Oh, okay, we can't ensure that.
So that is the one which I'm looking at. So when we started with rotational convolution or vector CNNs, one of the things what we said is that it is rotation invariant. Now, in order for it to be rotation invariant, it needs to take it from here and then create rotated versions of it. The only difference which came down from last class to this class is that in the last class we were taking our inputs as scalars. So your a scalar field, your weights were also scalar field, but then you generated a vector field. Now in the first layer you will always get a scalar field as an input. And then you can once your vector field is generated, when you go to the next layer, You will have to get all of these vectorized operations working out.
Yes.
Okay. So now from here, let me ask you this question. So I'm drawing a network and you guys will have to tell me what is the space complexity being required at every single layer over here. Okay, so this is what I wrote down. Now let's understand this one. So my input over here is X. Okay. Now I take that X and I'm convolving with these weight kernels over here. Now the question is that say my weights over here is some of some particular size. Okay. So say the spatial span is I cannot use W and H. Maybe I can just use WH. The spatial span is WH. Now tell me like what will be the other dimensions over here? So what will be the size of each kernel?
Sir, is it 3?
4 by 3 by W by H.
So this is what it is going to be. Okay. Now what will be the size of this bias B1? What will it be for B1?
So for B1 it will be, is it
4 cross WH.
4 cross 1. Why will it be WH? There is a bias for every single convolution kernel. There is not a bias for every position in that kernel. Okay. Now when I get this output vector field, what should be the dimension of that tensor? So how many channels will be there in that tensor?
4.
4 channels. Okay. Then
4 by 2 by
then
W by H.
so say some f dashed cross n dashed, and your m dashed is going to be the same as what? M minus w plus 2p divided by s plus 1, right? And n dashed is equal to n minus h plus 2p divided by s plus 1. Am I correct? So basically you are operating with a stride. So this is PW, this is PH, this is SW, this is SH. So with whatever stride and pad you are operating, I'm just doing it with that. Okay.
Excuse me, sir.
Yeah.
So one question here. This Z is R 4 cross 2, sir. Why this 2 is coming? This I didn't understand.
So look over here. Z is a vector field. Now a vector can be represented in two different forms. Either it is say the magnitude and direction. In that case, you would need two scalar numbers, or it is represented in UV format, which is horizontal component of the vector and vertical component of the vector. In that case, also you will be needing two different scalar values over there.
So it is in 2 dimension, right?
So what will be the dimension of this tensor over here? You need two scalar values.
So one will be in horizontal and one will be in vertical. So that is where
Yes.
2. Okay.
Yes.
Okay. Yes.
Either horizontal vertical or even rho theta. Even if it was rho theta, then also you would need two different scalar representations.
In cylindrical coordinates.
What?
In cylindrical coordinates, if we are taking rho theta.
Yes.
Okay. Yes, sir. Understood.
Okay. So now here that you have got your Z. So now let us begin with this Z over here. So what I have this Z which belongs to R to the power of say C number of channels cross 2 cross M cross N, and then I convolve it with some different number of convolution kernels. Just hold on a second. So these ones I can write it as W21, W22, W23, W24, W25. And this is B21, B22, B23, B24, B25. Okay, so this is going to give me a bunch of such fields. No, right. This will not come. And I can take all of them, run and orientation pooling, and then come up with a vector field version over here, which I call it. So this one is Z1, this is Z2. Okay, so now here, if this W2 is essentially this collection of W21, W22 up to W25. In that case, what is the size of this tensor? What will be the size of this tensor W2? Because remember, this is a vector field.
5 cross
This is also a
C
vector
cross
field.
W cross H.
5 cross
C cross W cross H.
think again.
5 cross C cross W cross A cross
5 cross C cross 2 cross W cross H. The reason is because this is also a vector field. And what will be the resultant output Z2, the size of Z2 over here? What will be the size of Z2?
5 cross 2 cross
output?
M dash cross N dash.
Okay, good. And then for B,
So 5
what will be
cross
the
1.
size of this will be 5 cross 1. Yeah, because that bias anyways is always a scalar value over there.
Sir,
Yeah.
I have a question. Like, can you give an example of that input dataset where the size of like there will be a vector input in this like 2 cross and a real
The input will never be a vector. You need to keep this in mind. What you will have is the input is scalar, but so you have a convolutional neural network. So there are multiple convolution layers. So the input to the first layer, this is why we were solving it in this way. So input to the first layer was a scalar x over here. Okay. Now what this produces, so this input to the first layer, which is a scalar, this goes through vector convolution in order to be rotational invariant. It produces a vector field. See, this is why it's a vector field over here. Now this output can be sent to the next layer, which I see over here. So this is my output from the first layer, which comes over here. Now here this becomes a vector field. So my data, this did not reside in my data set. In my data set, I anyways had only that scalar field image over there. But the output of the first convolution layer with a vector convolution generated this kind of a vector field. Now from this one, I will be convolving it with vector fields itself, because all of these values are vector fields. They need to be vector fields, otherwise it will not. And then on, it keeps on generating these kind of vector fields. So now does that make it clear to you?
Yes, sir.
Okay, so that's all what I had about this one. I mean, you can practice. You will be given some assignment to practice out on this one, and you can practice further on this. So that's where I will close with my vector convolution networks. And then tomorrow onwards, I will be starting with semantic segmentations and more of like full scale image to image conversion networks, how they would be working. Okay, so is that good with you?
So one question.
Yeah, tell me.
So what is the dimension before Z2, like before the orientation pooling?
What is the dimension before the orientation pooling? Okay.
Yes.
Because they are not transparent, so I'm not looking into that one. So you mean to say like what is this one with the operational space, right? So this one, let me use a different color. So this field over here, this will be a scalar field. Okay, because everything is corresponding to every location. So this one is scalar. This is r to the power of m dashed cross n dashed. Similarly, this is also r to the power of m dashed cross n dashed. Now, when you pool across all of them, that will go and create one of the channels over here. And that one single channel which you get over here is r power of 2 cross m dashed cross n dashed, because this orientation pooling leads to creating a vector field over there. And then from each of these things you will get a different layer. So from here you will get down the next layer. Then from here you will be getting down another layer. And then like this it keeps on aggregating, and that's how you end up getting this 5 cross 2 cross m dash cross n dash.
So if Z1 is vector or scalar, that does not it will not affect the space of this.
The reason it will not affect is over here. So wait, where did it go? Over here. So the output of Z, if the input Z is vector and the W is also a vector, still the output defined by a convolution, which is essentially a dot product between two vectors, is going to be a scalar. See, this is how we define vector convolution.
Okay, sir.
For generating the gradient function, what does it G signify?
G is not the gradient, G is the transformation, if you recall. So in the previous class, what we had done, so you have some sort of a transformation over there. The transformation is what we call as G. So transformation in terms of rotation by an angle theta is called as G theta.
Yes, sir.
And inverse of that will be G minus theta, let's say.
Hello, sir.
Yeah.
Sir, in this slide, just I had one small doubt. Like, sir, g of minus theta. Sir, the logic over here for using minus theta is just to compensate the kernel being rotated by theta, right, sir?
Yes.
Okay, so that is why like the minus theta is basically counter effect, doing the counter effect of the earlier rotation, right, sir? So this is the entire logic.
Yes.
Okay,
Yes.
this is the point. Thank you, sir.
Okay, guys, then let's close for the day, and tomorrow we will begin with semantic segmentation.
And sir, regarding this, like this calculations, will we be given some sort of worksheets to carry them out, sir? Because like seeing them and working
Yeah,
them
yeah.
is
No,
helpful.
there are more worksheets coming so that you get a grasp of this one.
Okay, sir, because like seeing them out here and just follow, comprehending to them is a bit difficult. So that's why working them out will be helpful.
No, I'm going to give you worksheets, but separately, my advice is that you guys start coding it down. Once you code it down, then it will be very clear to you.
Yes. Okay. Okay. Sure.
It takes time to get used to these ones.
Okay. Thank you, sir. Thank you.
Okay, see you guys then. Let's close for the day.